So, different setting again. It's really cute. I know. You can thank Miss Mena for that. All right, I have a board. We're doing things. Okay. I hope everyone's doing well. I hope election day didn't stress you out too much, and I hope that that you learned something from this video. And let's just get at it. Okay. So right here we have our general form. All right. Actually, let me talk about what we're going to be doing today. Today I'm basically just going to summarize everything. Yeah? Okay. I think I'm going to try to fill in some gaps that maybe we didn't understand before, and I'm just going to go over the transformations of the graphs. It'll all be good. It'll all be okay. So where are we going to start? We're going to start with our general form. Well, we know our general form is y equals a f of bx plus c plus d on the outside. Yeah, it's all color-coded here beautifully. So as you can see right here, a plus f of x, or f of bx plus c plus d. Notice b and c are on the insides of the parentheses. A comes in the front, it's the coefficient in the front, and then d plus d, that's on the outside, right? Now what's f of x? What does f of x represent? F in this circumstance is just any of the trig functions. So sine, cosine, tangent, cosecant, secant, cotangent. You replace that with f, okay? Cool. So far, so good. So let's talk about what these different letters represent, right? So A is our amplitude. Okay, so that means if we're looking at a sine or cosine graph, and subsequently if we're looking at a cosecant and secant graph, because we know that to do cosecant and secant, we need to know how the sine and cosine graphs look like, right? So we're looking at those four trig functions. Amplitude is basically how high or how low we're going based off of that midline on the graph, right? Because we know that for sine and cosine, that is a sinusoidal wave. It just goes up and down. Well, amplitude tells us how high are we going and how low are we going, all right? So that gives us our y coordinate for how high and how low this wave goes, right? Okay. Amplitude for cotangent and tangent is a little bit different. Amplitude tells us where those two outside invariant points are. So I'll go over that a little bit in a second later, but just remember that tells us where the invariant points are. So we have a central point on the graph, and then our invariant points are either below or above, and just like with amplitude, that'll tell us how high or low those invariant points are. Again, we'll go over that more in a second. But just remember, amplitude tells us how low or how high, okay? B, that helps us find the period. Now, if you remember, right, for a sine, cosine, cosecant, and secant function, right, our B helps us find the period by plugging in P equals 2 pi over B. Now, hopefully, if you watch the tangent videos or if you paid attention in class, you know that for tangent and cotangent, finding the period is a little bit different. It's P equals pi over B. So it's not 2 pi anymore, it's pi. And why is that? Well, because for y equals sine of x, right, so that just basic trig function, y equals sine of x, our period for that is 2 pi. All right, remember when I showed you how to plot the original sine function, we went over the entire unit circle. Well, the entire unit circle is 2 pi radians, right? Yes. That is why that one is 2 pi. Now, when we graphed the tangent function, we didn't look at the entire circle. We looked at half of the circle, remember? So we plotted 0 radians, pi over 4, pi over 2, and then we went negative. So we plotted 0, negative pi over 4, negative pi over 2. So we took a look at half of the circle. Well, half of a circle is only pi radians. So that is why when we plug in this formula, we do P equals 1 pi, just pi divided by B, okay? Again, if you need more clarification on why that is the case, watch the videos, they're all there, okay? Then for C, we know that that's our phase shift, right? So that is our horizontal shift of the graph, all right? When we're talking about sine, cosine, cosecant, and secant, that is going to help us find out where our little period actually starts on the graph. So where this wave is. We remember that, hopefully we remember that sine, the graph starts at the origin, and we'll go over this again in a second, just as a reminder, quickly gonna say, right? Sine starts at the origin, so if we have a phase shift, that means that that central origin point is moving horizontally either left or right. Okay, same thing goes for cosine, right? We would normally we wouldn't start at the origin, we would start a unit up, but again, that where the period starts, it shifts left and right, okay? Again, we'll go over that again in a second. But when we're talking about tangent and cotangent, C, when we're talking about that phase shift, Well, for tangent, that phase shift is going to tell us where that central vertical line is shifting to the left and to the right. Again, we'll go over that in a second. And for cotangent, it actually tells us where our first, what's the word I'm looking for, where our first vertical asymptote starts, okay? And that should be reviewed from today because that's what we're talking about today, is how to do the transformations of tangent and cotangent. So you'll see a little bit better how this phase shift applies to tangent and cotangent, all right? And then D, the vertical shift. This is the same for pretty much everything. It's right on the outside. All you're doing is just moving the graph either up a couple of units, so you're changing the y value up a couple units or down a couple units, and that goes for all of the functions. That one's pretty simple. I think that one's the easiest one to graph. It's just, if the graph is here, are we moving it up or are we moving it down? That one's straightforward. That one pretty much stays the same for all of the functions, okay? So let's take a look at sine and cosine real quick, just so that I can do a little bit of clarification on that and what those periods are supposed to be looking like. So let's pause. Okay, so here we're just looking at the standard y equals sine of x graph and y equals cosine of x graph. Now, I had some people tell me that they think that the cosine graph looks less curly, or not curly, but less wavy. And I want to prove that that's not the case. This is equally as wavy as this. These actually have the exact same components. So let me show you what I mean. Let's break this graph down into quarters, into little cells. We'll call them cells. So here, right here, if we've made a little line, right? Here's 1, 2, and let's make a little line right here, 3, 4. So these are 4 little cells of the graph. Notice right here we're above the midline. So here's the midline, right? Here we're above the midline and the graph is increasing. Here we're above the midline and the graph is decreasing. Here we're below and the graph is decreasing. Here we're below and the graph is increasing. We actually have all of these same little cells inside of this graph. So here, this would be like our number 2 right here, where we're above the midline but we're decreasing. Down here is like number 3. Over here is like number 4, and this is like number 1. These are the exact same graph. We're just looking at different phases of it, if that makes sense, right? So here we're going 1, 2, 3, 4, and here we're starting 2, 3, 4, 1. And then again, you would repeat 2, 3, 4, 1, 2, 3, 4, 1, which when you combine those together, they actually look exactly the same. So it's not that cosine is less wavy or anything like that. It's just that you're looking at a different section, right? So here, if I extended this graph up and I cut this little one out, this would be 1 again, and now we're looking at a cosine graph. That is how these two relate. They're the exact same looking graph, just at different parts of the graph, okay? So I wanted to clear that up, okay? Now, let's really quick just talk about these, a couple other elements of this graph that are happening right here, okay? So, notice that I have 5 points plotted on each of these graphs. Let's do this in a different color because I have color options now, so why not?
Amazing.
Amazing, I know. An innovator.
Visionary.
So here we've got 1, 2, 3, 4, 5 points. 1, 2, 3, 4, 5 points. All right, it's hard to tell because I did it in blue, but that's okay. All right, we got 5 invariant points. PTS means points. Here we've got, again, the same 1, 2, 3, 4, 5 invariant points. Yeah? They're the exact same points, just shifted, right? So, the thing that I want to mention is, right, the period spans between these 5 points. In the middle, right, this third point right here, this is like your little midpoint, and the same thing would go here, right? So here's 1, here's 1, 2, or 1, 2, 3, 4, 5, right? This is one period at our third point. That is like your midline, and you know that your other invariant points become in between, right? They come in between. So this point right here is equidistant from the beginning of this period to the middle of this period, and this one is also equidistant. Basically, we're just cutting up, just like I did, we're cutting up the graph into fourths, okay? That's all that's happening here, right? And then this point right here, and this point right here, these are like the peak, right? This touches our range. And this peak down here, not peak, I guess I should call it a valley, this is also the other end of our range. Right? And then we would use those little peaks and our valleys, our invariant points, to create our cosecant and our secant graphs. So let's do this in a different color. So here this. So here's cosecant, because if we remember, right, if we're looking at a fraction, cosecant is 1 over sine. Where the denominator increases, the fraction decreases, right? So as sine gets bigger, cosecant gets smaller. As sine gets smaller, cosecant gets bigger, and the same thing applies for both, right? And then this would be a vertical asymptote because we can't have 1 divided by 0, so where sine is 0, that's an asymptote. All right? So here in pink, you can see cosecant of sine. And that's how you would create any cosecant graph. Just graph it as if it's sine, and then just add in those invariant points, right? Make sure those touch. Add in your little asymptotes, and just draw in the little curves, the little outside curves. They're like shoelaces or something. I don't know what to call them. This is like a wave, tangent looks like a snake, and I guess I don't know what to call those, but you get the point. Now, similar principle, right, with the cosecant, except, right, this is where our point is now, right? These are our invariant points. So it looks like, everything's ugly, sorry. So it looks like that over here, where this is 0, right? And if I extend this into infinity, then I would create something like this. And it looks exactly like the cosecant graph. Let me write this out. Secant equals 1 over cosine, right? It looks exactly like the cosecant graph. It's just shifted. We're just looking at it. It's just shifted. That's all it is. So that's why like sine, cosine, secant, cosecant, those all kind of work together. They work pretty similarly, okay? Now if we're talking about the actual shifting, right? Here, let me erase this action. You can pause. Okay. So let's talk about the different translations real quick. So, right, we talked about y equals a f of b f. Okay. All right. So if we know that our general form is y equals a f of bx plus c plus d, let's take a look at a. A is our amplitude. That means how high or how low are we going. All right. So let's say we're taking a look at y equals 2 sine of x. All right. Our period is not changing, so that means that these 3 invariant points are staying exactly where they are. We're not stretching this in any way horizontally. But we have this 2 as the coefficient now, right? Remember before we had an implied 1, and that is why we had our range of 1 and negative 1. But now we have a 2, okay? So that means that this graph is now going to go up 2 and down 2, right? So here's positive 2, here's negative 2. So this graph is now going to look like that. You see? So that's what the amplitude is. How are we stretching this graph in the vertical direction, both positively and negatively, right? That's all that means. All right, and the same thing goes for cosine over here. So y equals 2 cosine of x, right? So instead of this being at 1, now it's going to be at 2, right? This is going to stay the same, this is going to stay the same. Now this bottom peak, or not bottom peak, bottom valley, instead of being at negative 1, it'll now be at negative 2. And this peak right up here again will also be at 2. Again, we're not changing the horizontal nature of it all. The period is still 2 pi, right? And we still have our cells, right? Here's the first cell, the second cell, third cell, fourth cell, second cell, third cell, fourth cell, first cell, right? Just like I numbered them before. That's what A looks like. Now, let's talk about D. Pause. Okay, so the reason I'm doing D next is because when you're taking a look at the sine, cosine, cosecant, and secant graphs, I want you to actually graph it in this order. So A, D, C, and then B. I think that this is a helpful order to go with, so that's why. That is in a flow chart. I created a flow chart, so you should take a look at that. But now we're going to take a look at D. Okay, so right, we did A, now we're going to do D. Cool. So D is going to tell us how much this graph shifts up and down, right? So let's say we have y equals sine of x plus 1, right? Plus 1 on the outside. That means that this whole midline is just going to shift up 1 unit. All right, so this line is now going to be here. All right, so where before it looked like this, now it's going to look like this. You see each invariant point, every single one of these 5 invariant points moved up 1 unit. This should actually be on the line. All right? Every single one of these 5 invariant points went up 1 unit. Now, same thing goes with cosine over here. So if we have y equals cosine of x plus 1, right, this invariant point goes up. This entire midline right here is going to go up, right? And this point right here is going to go up 1 unit. This point is going to go up 1 unit. This point is going to go up 1 unit. This point is going to go up 1 unit. And we are going to create something that looks like that. All right, the whole thing has gone up 1. That's what this right here, this D at the end means. All right, pause. Did you press play? Okay. So next we're going to do C, right? So what does C help us find? C helps us find our phase shift. Oh, I wrote this actually incorrectly. Haha, my bad. So let's say we're doing x minus pi. Or x minus pi. So notice, right? This minus x, this is on the inside of the parentheses, all right? That's how we know it's C, okay? Now all we're going to do to figure out our phase shift is set this inside, right? X minus pi equal to 0, and we're going to solve for x. Well, here in this equation, pretty simple. All we have to do is add pi to both sides, and we get that x equals pi. Cool, so that means that because it's positive pi, we're going to move to the right pi. That's all. That's all that's happening. So we are taking this graph right here, and we're moving the entire thing pi to the right. This is positive, so that's why we're moving to the right, right? So that means that now, let me write this in, x equals pi. Okay. This whole graph is going to shift pi units to the right. Notice I've labeled my units pi, 2 pi, 3 pi, make it convenient for everyone to see. That means it's now going to look like that. So that means this invariant point has shifted pi units, this invariant point has shifted pi units, this one right here has shifted pi units, this one right here has shifted pi. Yeah? Okay. Okay. And this one too. All 5 of the invariant points have shifted pi units to the right, because this is positive pi. Notice that yes, in here it is minus pi, but when we solve for x, we find that x equals positive pi. That's why you need to solve for x, so that you don't get that fact confused. So that means that if we do the same thing over here, right, every point is going to shift pi units. Right, so this graph is going to look like that now. So that's what a phase shift really means, and hopefully these arrows help you see that we are just literally shifting this graph, right? We are shifting the phase of the graph over to the right or to the left, horizontally. That's what a phase shift is. Now let's talk about B, last but not least. Pause. Action. All right. Last but not least, we're going to talk about B in here. So that helps us find the period. Now we know if we're looking at sine, cosine, cosecant, or secant, right, that we're going to be looking at the formula P equals 2 pi over B. So that's exactly what we're going to do. Here we have, right, the coefficient in front of the x is 2. So we're just going to do P equals 2 pi over 2. The 2 cancels out, right? So P equals pi. Great. That means that our period, right, the amount that this little wave stretches is no longer going to be 2 pi, but it's going to be pi. Let me show you what that looks like. Nothing is changing vertically, but things are changing horizontally. So what is now happening is that our first and our fifth invariant points are now going to be 1 pi unit long, right? So here's the first, here's the fifth invariant point, right? So what would have been the third invariant point is now in the middle. What would have been that first peak is now going to be in between those, and what would have been the bottom valley is now going to be in between the third and the fifth, right? And we are squeezing this entire graph. That is what that means when we're changing the period, all right? We're squeezing this all together horizontally. And that's why I said it's like stretching out or squishing in a slinky, right? That's what's happening here, okay? So that is why these like little invariant points, these 5 invariant points, really matter a lot, because they help you figure out how much you need to stretch or squeeze this in, all right? And now this is what it would look like over on, actually I drew this really poorly over here. Imagine that this right here is 2 pi, okay? So over here, right, we know that our period is no longer going to be 2 pi, our period is going to be pi. So that means that all of the action is going to be happening in this little section instead of over 2. Okay? We're squeezing it, or we're stretching it out, right? Sometimes if this coefficient in the front is a fraction, right? So like let's say this is y equals sine of half of x, that's actually going to make your graph like stretch out a lot more. Okay? So instead of squeezing in, it'll stretch out. Okay? And that is why we do b last, because that is like the most annoying part of it all, but once you get that down, you know that the period repeats over and over, so this is going to repeat like this for infinity and negative infinity for your domain, and this is going to repeat like this. And wow, look it, they're like the same graph, because I've told you so many times that they're the same graph, just shifted. Wow, okay. That's enough of sine and cosine. Let's really quickly just go over secant and cosecant so that becomes clear for all of you. So let's pause.
Okay.
Okay. As a reminder, right? These are our reciprocal functions. Cosecant is 1 over sine. Secant is 1 over cosine. That means if you are given a function that is either cosecant or secant, start off with the sine or cosine. Graph it as if it is sine or cosine. So if I give you something wacky, right, like y equals 2 secant of 1/2 x minus pi plus 3, something crazy like that, start off by just drawing this out, because secant goes with cosine. Draw it out as if it's a cosine graph. Draw it out as if it's a cosine graph, all right? And then all you have to do, imagine this is, I don't even care about the numbers right now because I want you to get this conceptually, right? Imagine this is the graph that you're given. If you want to find the reciprocal, all right, this is all you have to do. So this would be like sine of something, right? All you have to do is wherever, right, there's this first, third, and fifth, right? So here's our invariant points, right? I'm sorry, it's drawn pretty poorly. I kind of sketched it really quickly. But wherever we have this first, third, and this fifth invariant point, those become vertical asymptotes. All right, so same thing goes over here. It's going to repeat. Okay, that's super ugly, and I'm sorry, but those become vertical asymptotes. Not here, actually, I lied. Right? So just where sine equals 0, right? Those become vertical asymptotes, and then you are just going to meet, right, this second and this fourth invariant point, and you are just going to draw the reciprocal, all right? That's all you have to do. Don't overcomplicate it in your head, okay? You do not have to draw them separately. All you need is the information from sine or cosine. All you need, I will repeat this again, all you need is the information as if it is sine or cosine, and you can do the respective cosecant and secant graphs, okay? Because these secant and cosecant are both based off of sine and cosine. That's all. Don't overcomplicate it in your head. So if you see a general form that has cosecant, graph it as if it is a sine function, and then add in the reciprocal. If you see a function that has secant of something, graph it as if it is cosine, and then do the reciprocal. Okay? That's enough of those 4 functions. Let's move on to tangent and cotangent, and then we'll be done. Pause. We good? Okay. So just like before, when I was saying that you can use the original function to graph the reciprocal, that's what's happening here, right? So here's tangent, here's the reciprocal function, cotangent, all right? Now, we actually get this based off of this. And how do we do that? I've said it like 4 times already for all of you, but that's okay. We'll keep saying it again. Wherever tangent is equal to 0, right? Because cotangent is equal to 1 over tangent, right? Wherever tangent is equal to 0, that becomes a new vertical asymptote because we cannot divide by 0, that is undefined, right? So tangent is 0 right here, where x equals 0. So now here at this, right here at this line where x equals 0, that is now undefined for cotangent. That is now a vertical asymptote. Same thing happens over here. So now when we're over here and the x, right, that becomes another. Okay? And now, just like we said before, whenever the denominator increases, the function decreases. So wherever tangent is increasing, cotangent is decreasing. Okay? Cool. So now let's actually talk about the different phase shifts really quick. Okay, so just like for amplitude, right? Before we talked about different invariant points. Okay, tangent and cotangent also have invariant points. I will show you them right. Oh shoot, I'm gonna mix up the colors. All right, the invariant points for tangent and cotangent are right here. There's 1, 2, 3. Notice the way that these are lined up makes this graph increasing, right? This right here, between these 3 points, this right here, that's a positive slope. That's how we know tangent is increasing. The invariant points for cotangent, here, let me draw this a little bit better. It's not much better. Are right here, and right here. This is not drawn to scale very well. I'm fixing it now, right here, okay? So there are 3 of them, 3 invariant points for tangent and cotangent. Before we looked at 5, now we got 3. 1, 2, 3, let's not worry about that because that's a different period, okay? 1, 2, 3. So let's say we're talking about, actually, so remember how for sine, cosine, secant, cosecant, I said that the order you're going to go in is A, D, C, B. You're going to do a different order when it comes to tangent and cotangent. I think it's a lot more helpful this way, so pause. Okay, so this is the order that I want you to go in when you're graphing tangent or cotangent. C, B, D, A. That's what you're going to worry about first. So here we're going to start with C first. So that means we're actually going to start with the phase shift. All right, so let's say we're taking a look at y equals tangent of x minus pi, just like we did before, and then also y equals cotangent of x minus pi, all right? Well, if we take the middle right here, right, yeah, I'm going to erase all of these extra guys so that they're not in the way. If we take the middle, right, in the parentheses, x minus pi, we set it equal to 0, x equals pi. Cool. So that means we're going to shift this whole graph over pi units. Now, if you remember, right, this right here is pi over 2, this right here is negative pi over 2, so this is going to shift, here's 1 pi, 2 pi, this is going to shift over a lot, all right? It's going to shift over all the way over here. Okay, so this is the graph. This central point now, right, for our tangent, this central point is now going to shift over positive pi units. So that means we know the graph is going to look something like that. So this central point is now shifted, all right? Now notice, right, that means that for phase shift of tangent, that changes this central point where tangent equals 0. Well, what does tangent equals 0 mean for cotangent? Well, that's where our vertical asymptote is, right? That is why right here at x equals 0, that is the first vertical asymptote. Well, if this central line is the vertical asymptote, on this side, that means that this vertical asymptote, right, for this phase shift, is going to move over pi units. So that means the first vertical asymptote is now going to be over here. That's what C helps us find, okay? The phase shift, right? How much is this moving side to side? Well, now we know this graph is going to look something like this, and we know that this is shifted over. This is actually going to go over that way. I don't have enough space on the board, and I apologize for that. But that's what we're doing for C. All right, so for tangent, the phase shift shifts the central line. For cotangent, that phase shift is going to change the first vertical asymptote, right? Because where the central line is a vertical asymptote for cotangent, all right? Central line of tangent is the vertical asymptote, the VA, for cotangent. So if we would have shifted this central line over, so now this central line is like over here or over here, whatever, that has now shifted the vertical asymptote instead. All right, this is super duper ugly, but that's okay. Let's keep going. Let's talk about B now. Pause. All right, so if we remember before, right, the period for the tangent graph is not 2 pi. Remember, because we only took a look at half of the circle. The period for the tangent graph is pi. Why? Because going this way is pi over 2, going this way is pi over 2. So pi over 2 plus pi over 2, right, is just pi. Yeah? Okay, so the graph for the period, right, it's just pi. And the same thing goes here. You can actually see it, I think, a little bit more clearly with the cotangent graph because we're starting at 0 and we're going to pi units. Yeah? Okay. So that means we're calculating the period right here for b, right? It's no longer pi of 2 pi over b, p equals 2 pi over b. Now it's p equals just pi over b. So let's say we're given tangent of 2x, right? That means that our period is now going to be pi over 2. That was super duper simple. Same thing goes with tangent or cotangent. So if we're doing cotangent of 2x, we're going to plug that in, p equals pi over 2. So that means that this is actually going to expand over pi over 2 units. So now this is going to be pi over 4 this way. This is going to be negative pi over 4 this way. Why is that? Because pi over 4 plus pi over 4 is pi over 2. And that means now we're going to get a much skinnier looking graph. That's kind of ugly and hard to tell. Sorry about that. I'm rushing a little bit. I just need to breathe. Yeah? Right.
You have 3 minutes.
We got 3 minutes. We're going to get it. All right? And the same thing is going to apply here. So no longer are we actually going to have it over pi. We're going to have it over, I think it's a little easier to actually tell here. We've shrunk this graph, we made it a lot skinnier. So that's B. That's what B looks like. Now, let's take a look at D. I think that this one's super simple, so let's pause. All right, so if we're talking about D, all we're doing is taking the central line and shifting it up or down. So if we're looking at tangent of x plus 1, all we're doing is taking the central line, shifting it up, and this becomes our new graph. All right, same thing. Cotangent of x plus 1, we take this central line, we shift it up 1, and now this is our graph. That's all that's happening there. That one's super duper simple. Now let's talk about A. All right, pause.
Okay.
All right, and now for A, that's our amplitude, right? We know we have 3 invariant points, right? For so 2 tangent of x. I have no time right now, guys, but all we're doing here is instead of this being 1, right? This is now going to be 2. And this point right here, instead of being 1, it's now going to be 2. So that means that our graph is going to look something like that. That's all that's happening, right? So here, where it would have been 1, now it's 2. Or shoot, now it's 2. Where this one is negative 1, this is now negative 2. So our graph just looks something like that. And that's the amplitude, all right? You're just going to be moving that first and third invariant point on your regular graph. And make sure, again, that for tangent, it's increasing. For cotangent, your function is decreasing. That is so much. That is so fast. I'm sorry, but we got to get to class. I have my class at 11 a.m. right now.